the fourth lecture on Lagrangian mechanics. In the last class, that is in the third lecture, we have shown that the Euler-Lagrange equation remains invariant if we add the total derivative of the gauge function to the existing Lagrangian, so that the resulting Lagrangian also satisfies the same equation. Furthermore, we have shown that under Galilean transformation, Euler-Lagrange equation remains invariant. In this class, we shall prove that the Euler-Lagrange equation is also invariant under a general coordinate transformation. Firstly, I want to see state what do we mean by general coordinate transformation. We may describe a system in two coordinates. There may not be any relative motion between the coordinate system as we have taken in Galilean transformation, or there may be some relation. The main thing is that the same system may be described by two sets of coordinates. One is qi, which we say when we express it in S basis or S prime, the quantities are qi's, the positions and time t, which gives us the Lagrangian as function of qi dots and of time t. We can also express it in another basis S prime, in which case this is qj prime time t, and we have Lagrangian L prime, which is a function of qj prime dots and t. So this is the generalized velocity in S basis, generalized coordinates, generalized velocities, time. In S prime basis, this is generalized coordinates, generalized velocities and time. We want to show, we shall show that the same Euler-Lagrange equation is being satisfied in both the frames. Let us consider the Euler-Lagrange, in this frame, the Euler-Lagrange equation that is being satisfied is del L del Q K del L del Q K dot minus del L del Q K is equal to capital QK, where capital QK, which we shall introduce in the next class, is called the generalized force. Capital QK is defined as summation over I is equal to 1 to n if I dot del Ri del QK is the generalized force. Note that since QK may not have the dimension of length, so as in small qk, the coordinates, capital QK may not have the dimension of force, but if we write this quantity QK times QK times delta QK, delta QK, indeed it has the dimension of work. It has the dimension of work. This is the requirement. And here this QK term arises when there are some non-conservative part present. We have already introduced this part that for conservative system this is the dPdt and this is as if the force. This is another representation of force which takes into account the non-conservative part. Our aim is to show that L prime also satisfies an equation of this sort, where L is replaced by L prime, Q is replaced by Q prime, small and capital Q's are replaced by this. We first see how these transformations are related as we move from one representation to another representation. Say for example, we have a particle moving in 2D. We may represent it in terms of Cartesian coordinates x, y, z and time, and we can as well represent the state of the particle in terms of r theta phi. So this is the Cartesian basis and this is the spherical polar basis. Now in general, the coordinate transformation is related like this. Qi is related as function of qj primes and of time t, and on the other hand the inverse transformation is qj prime is equal to qj prime as a function of set of qi's and of t. As an example of this, let us consider the Galilean transformation that we have considered earlier. Xi is equal to capital X0 plus xi prime. You recall the representation, the transformation in terms of vector, it was R0 plus Ri. So this is the representation where x0 can be written as v0 x t plus xi prime. So this is the transformation. Xi is related to xi prime and t. It is a very special type of representation. We can transform from one basis to another basis. We can make a transformation from one basis to another basis. Let us calculate qi dot. This quantity qi dot, this is equal to ddt of qi. This can be written as del qi del t plus summation over j is equal to 1 to n del qi del qj prime dot. This is the transformation relation. Here we have used the fact that qi is a function of qj prime and of t. So there is no dot, del qi del t. One thing immediately follows is that if we differentiate this del qi prime del qk prime dot, then this is del qk prime dot operating on del qi del t plus summation over summation over j is equal to 1 to n del qi del qj prime Now the coordinate transformation does not involve velocities. It is as per our assumption. So this part is 0 and this part is also 0, and we are left with only term that j is equal to 1 to r and del qi del qj prime delta qj prime delta. This is obviously a delta function, so we have summation over j is equal to 1 to n del qi del qj prime is equal to delta jk. So this is only term will contribute when j is equal to k. So this is del q I del q k prime. So we see that this is the result. This will be used in future derivation del q I del q k prime dot. Another thing is that ddt del q I dot is equal to another thing is that del q k prime q dot is equal to ddt of del q I del q k prime. So now we shall study what is the Lagrange equation, Euler-Lagrange equation takes place in prime time. So first we consider del L del q k prime. First thing, L prime is when we transfer it into S prime, the quantities related to S prime, we have del L del T del q k prime plus summation over j is equal to 1 to n del L del q j del q j del q k prime plus del L del q j dot see one thing. Here we have used this quantity del L prime del q k in terms of the quantities relating to S prime, and the signature of prime will be through this del q k prime. So L is a function of T qj and qj prime. So we use j suffix for, it is better to use I suffix over here. That will create less confusion because we are maintaining the same thing, that S prime we use the dummy suffix as I, and in S prime we have used the dummy suffix as j. Now you see that time does not depend on the coordinates and from the relativistic theory, so this is 0, and furthermore and these two quantities we can change this one by use of this property to the j, sorry, there is another change, j. Sum over j is equal to 1 to n. We have del L del q I sum. I changed this summation from j to I. So this is I to n. This is I. Del L del q I del q I del q k prime. This is first term, and for the second term I write it del L del q I dot. Then this term is ddt of del q I del q k prime. And we calculate the similar thing, del L prime del Q K prime dot. The same thing will be there, only QK prime will be replaced by QK prime dot. So this is del L del T del T del Q K prime dot, which is obviously 0, plus summation over I is equal to 1 to n del L del QI del QI del QK prime dot, which is 0 because the transformation relation does not involve velocity as per our assumption. And then we have del L del QI dot delta QI dot delta QK prime dot. So only this term survives, which we write it as summation over I is equal to 1 to L del L del QI dot, and this term, this dot of both on numerator and denominator is replaced by this relation as del QI del QK prime. Now we come to consider the quantity x, which is ddt of del L prime del Q K prime dot minus del L prime del Q K prime. Now the first quantity, this quantity is the time derivative of this. So there is a summation all around. First thing is ddt of this part. Qi dot del Qi del Qk prime. And for this part we use this relation, so both are negatives. So del L del Qi if we differentiate this, this will give you two terms. One is when ddt operates on this, keeping this unchanged. This is one term. Another thing is ddt operating on this, keeping this unchanged, which is exactly this term. So this term cancels out, and we are left with the term is that I is equal to 1 to n ddt operating on del L del Qi dot, and this term cancels, so this term sorry, there is another thing, del Qi del Qk prime minus this term del L del Qi which we take this part common and taken out of the out, so we have summation over I is equal to 1 to n ddt of del L del Qi dot minus del L del Qi times del Qi del Qk prime. This is summation over I. For this part we write Qi. This is I equation, this is Qi. So we have Qi times del Qi del Qk prime. Now coming to I definition of Qi. we introduced another suffix j, so there is I and j. For qi, this is fj dot del rj del qi. This is for qi. You note that this is a definition of qk. So qk if equal k, and this is k, and there is a dummy index. So qi, so qi is the denominator, and we have introduced another dummy index j, and then we have del qi del qk prime. If we sum over I, we have sum over j, then this is fi dot del ri del qk prime, and this is in qk prime. This is, as per this definition, is qk prime, the generalized force corresponding to the kth degree of freedom in L prime prime. So we see that x is equal to ddt of del L prime del qk prime dot minus del L prime del qk prime is equal to qk prime. So the Euler-Lagrange equation, which is this in S prime, is becoming thus, that is, the form remains invariant under general coordinate transformation. So we conclude that Euler-Lagrange equation is invariant under general coordinate transformation. In the next class, we shall extend our Euler-Lagrange equation to include non-conservative system. To be specific, in the next class we shall consider Euler-Lagrange equation as applied to non-conservative holonomic system. That's all for today.